All right, so we'll continue the discussion with thermodynamics, which is chapter 20. So in the last lecture, we talked about what thermodynamics, right? It is a study of energy and its transformation. Before getting into this chapter, we commonly talk about heat of reaction. So we know whether reaction is endothermic or exothermic based on the sign of our delta H, so change in enthalpy, okay? When we talk about thermodynamics, you can think of the potential energy change into kinetic energy. But in the sense of chemical system, we will look into what's so-called internal energy. Okay, so that contains the enthalpy part, and which is work, known as work, and also the heat part. So we generally know that from our previous knowledge on enthalpy, we know when you have something less than zero, that means it's an exothermic process. Why do you feel the heat? That's because the heat is transferred from a hotter area to a colder area, and that's why you can sense difference in temperature. Okay, when the delta E is larger than zero, that means the energy is absorbed from the surrounding in order for this chemical transformation to happen. And I know in last Friday we talked about all different laws. Honestly, I think it's more important that you understand what the laws are about rather than remember which one is which. The zeros law is basically, it's a balanced triangle. So if A equal to B and A equal to C, that means B equal to C. That is simple. And that also implied the temperature will go from the higher end to the lower end. And you have to do work if you want to go backward. That means going from the low temperature to high temperature. Okay, so the first law, when we set up the equation, this delta E equal to work plus the Q, and here it's talking about when we talk about our system and surrounding, the energy input and output are conserved. So energy has to go somewhere. But when it involves temperature change, you have to also consider the energy loss to your surrounding. Okay, so generally when we consider reaction, we care more about our system, but when we talk about thermodynamics, it's about accounting for all the energy transfer processes. So the conservation and energy, and such that energy cannot be created or destroyed. And the second law is a little difficult to understand, but you just have to remember that all the spontaneous process prefer an increase in entropy. And we'll get to the concept of entropy in a little bit because I know you guys haven't learned that before. For a reversible process, that means you can easily go forward and backward. That is the heat involved in such process, you can divide by temperature, and that describes entropy. So we can generally, from this equation, we know that the higher temperature, your change per Kelvin, it's smaller. And then the third law is a definition that a perfect crystal, it has zero entropy. So entropy, you can also think of it as a state function, the different states of your system. So this equation comes from statistical mechanics. So we know natural log of 1 is equal to 0, right? So that means when you have one state, you won't have any possibility. So entropy is dependent on the amount of substance that you have. So when we're talking about surrounding for a normal reaction system, the surrounding has air molecule, right? And if we only care about the content of your beaker, the beaker itself has heat capacity. It can undergo heat exchange. It can hold up some heat from your reaction if it's exothermic. Okay, so a lot of time you will see a circle, so that means it's standard state, because entropy could be a temperature dependent process, although sometimes we will make assumption saying that enthalpy and entropy are temperature insensitive under normal condition, which is 1 atm for gases and 1 molar for solutions. So we know the standard entropy has this unit. You simply divide by the number of molecules. Okay, so to better understand what I mean by microstates, you can think of a 4-particle system. They're color-coded. So there are total 16 combinations. As you can see, you can categorize it into 5 different states based on the number of particles that could present at any given time. So this is like a Schrodinger's cat, right? You won't know what happened until you actually observe it, and once you observe it, it is what it is. So we normally deal with grams materials, right? So if you divide by that by the Avogadro's number, then you will get a very large value. So we have a many particle system. We're looking at a many particle system. There's a lot of possibilities. So with 4 particles, you already have this many possibilities. And we know when we have reaction, it's about the collision and it's about the orientation of molecule. And we, from the kinetic gas theory, we know that gas molecule can move at different speed at any given temperature. So that means when you have a fixed temperature, it describes on average how much energy these particles could have. Okay, but some move faster, some move slower, right? So when we're looking at the smaller portion of them, when they collide, there's less tendency, less probability for them to induce reaction. But for the ones that move very fast, the reaction rate is higher. But when you take an average, right, we're looking at the ensemble. So a lot of times you'll see the word ensemble. That means count them all together. We're looking at the probability of, on average, how many of these molecules will collide and have reaction happen. So of course you can think about a scenario with even more particles, then you have more possibilities. So another way to understand entropy is entropy describes disorder. Okay, so the positive, when you have a positive value, that means it becomes more disorder. There's more room. The distance between particles are larger. Okay, so a lot of time people will refer entropy as randomness or disorderness of your system. For being more random, that you have more possibility, then that is the state. Okay, so this is easy to understand. The greater the number of possible microstates, okay, the greater disorder and the higher the entropy. So when we think about water freezing into ice, you're decreasing entropy. So that explains when you look at the heat involved to heat up a cup of water or melting a block of ice, you have to consider this phase change part, right? It's not just a simple heat capacity times the temperature change and the mass. You have to consider this phase change process. And such phase change process is the amount of energy that you need to give in so that the water molecule can gain entropy to become liquid or become gas from a solid state or liquid state. Okay, so now I want you guys to get together and discuss the following with your group members to predict the relative S of your system. So I sort of already gave you the answer for the first one, right? The higher the temperature, the gas molecule move faster, right? Okay, so I would like you guys to go through each of these cases. So here is want you to recognize or figure it out on your own whether the delta S is positive or negative for each of these systems. Or they're relative for the metal, and acid is for you to think about the relative delta S of these systems. Okay, so temperature change is easy to understand, right? The phase change, that also makes sense. So think about intermolecular forces of water or the structured water, such as ice, right? So you need to put energy into the system so you can break these bonds. Generally, breaking bonds involve release of energy, right? Making bond required input energy, right? But if you look at the surrounding, it's exactly opposite. When we think about dissolution of a solid or a liquid in water, we must consider its original state. And we know when we make up a salt solution, the most salt that are soluble would dissociate into ions, right? So once it becomes ions, it breaks off from the lattice of these crystals, so you gain a lot of entropies, right? And for water, the water has to form the solvate structure, okay? The water molecule will surround your ions. So locally, you are decreasing the entropy of water molecule for the ones that are surrounded by solute. So one very interesting example is there are some organic lives, for example, a frog, that can resist wintertime by having these anti-freeze proteins. So generally, the water will freeze, right? But the presence of these anti-freeze protein will change the melting point of water so that the crystallization process of water will become less favorable, right? So they can survive the winter. Okay, so then when we think about higher charged cation, like sodium chloride has +1, but if we have aluminum, it's +3, right? So the change of entropy is even more because you need more water to form a solvation structure for your metal ion. If we think about molecular solutes such as sugar, okay, so such as alcohol, right, then it's a different story. Although there's some hydrogen bonding, but it's really case by case, so it's really hard for us to predict unless they're extremely different. Then if we think about dissolving gas in liquid, we know that we decrease the amount of entropy, right? So that kind of explains why solubility of gas becomes higher temperature, okay? Because you have more energy to break away from the dissolution state, okay? So for the lithium, sodium, potassium, in your book, it's described it as heavier atom, there's more microstates. So because the bigger the atom, there's more these electrons, right? And we know these outer electrons, they have a probability of existing at certain regions. So the bigger it is, the more possibility. So you need to deal with more of these electron-electron interactions. If we think about a metal, right? They have these metallic bonds between them. They're not charged, but there are some interaction between their electrons. And for the HCl, HBr, the same rule apply. The larger the molecule, the more microstate it could have. And the important concept is the allotropes. So these are substances that have different structures. So if you think of a graphite, that's amorphous structure, and think about change of entropy. The diamond, we know, is a stronger material because it's crystalline. So for S, if you want to change the state of diamond, you will require more energy to break these perfect lattice. Okay, so I would encourage you to read page 905 when you go home. And there's also description on the number of vibration states, like we mentioned last lecture. And also I want to mention that if you have a ring structure, it generates limited the number of microstates that you have, because when you move one part of your system, it's going to affect the other part, right? So I mean, the one atom, you're going to affect the nearby atom. And generally, the longer hydrocarbon, because it has more of different orientation, we'll get to it when we talk about organic chemistry. Okay, so for each reaction, we can calculate the standard value for entropy. So when we do these calculations, again, it's final minus initial, and then we have to account for the number of mole, because we're talking, the unit is joule per mole per Kelvin. So we have to times the number in front of your molecular formula to account for the number of bond break or the number of bond form during such process. And we already defined S to be entropy or randomness or disorderedness of your system. So when your entropy increases, you have more randomness. We cannot predict the sign of this entropy change. Like we can draw a general trend, okay? We can reason it, but it's really hard to predict whether that will be positive or negative. Unless there's a significant change such as number of mole of gas, because the entropy for liquid and solid, this term is generally pretty small. So if we think about enthalpy, we generally think of it in kilojoule. It's 1,000 times more than entropy. Okay, when we look into entropy, we're talking about joule per mole per Kelvin. When we talk about entropy, we need to think about it more when we're dealing with gases. Okay, so this famous Haber process, ammonia formed based on these equations. We can conclude that it forms spontaneously, but slowly based on its reaction rate. For a reaction being spontaneous, doesn't mean it will go faster. So that's why we need to use catalysts in hardware process so you can lower the activation energy. So do not get confused. Delta G is related to activation energy, but it's not activation energy. So if we look at synthesis of ammonia, why I say it's formed spontaneous, what does that even mean? So spontaneous, that means it's energetically favored. Just like you prefer to sleep in instead of getting up on time for our Friday class, because staying longer time in bed is more of spontaneous decision or a spontaneous process, right? You don't have to move. So when you think about your messy room, it's gonna take a lot of time and work to put it into order. But making your room messy, it is a spontaneous process, okay? It just happened kind of on its own, and it just depends on the person. Some occur faster and some occur slower, and how come it becomes slower? Because having your room clean versus messy, it is a reversible process, and you have many microstates. So for some people who are more tedious about the organization, you put in a lot of energy little by little, so you reverse that entropy-driven process that caused your room become messy. Does this analog make sense? For ammonia, we know this entropy is negative because you are forcing many molecules to condense down, right? So it becomes less random. So that's what the sign of the entropy term means. When we want to look at the surrounding, we have system and surrounding. We can think of the enthalpy involved in such process or heat involving this process. We can relate these two terms because, again, entropy tells you the randomness based on the temperature increase. So at constant pressure, we can use enthalpy, that's heat, at the general term that you're familiar with. So when we're describing a system as whole, your reaction system and its surrounding, we will talk about the universe. So the overall ordinance, the second law of thermodynamics, suggests that it will continue to increase if a reaction is spontaneous. So that means they want to have more microstates. When we were talking about equilibrium state or chemical equilibrium, in the previous chapter, we have an equation that relate our equilibrium constant to temperature. And I know some of you asked, where did that equation come from? You'll briefly see that equation in a little bit. You can really use the concept of thermodynamics to explain such process. When we think about equilibrium, this means the concentration of reagent in your product doesn't change at infinite time. So because there's no driving force for this process to happen, that we can consider the heat or consider it from a standpoint of entropy. It's at its happy state. It doesn't want to have any change. So we would say the change of entropy is zero when it is at equilibrium. If you're far from the equilibrium or you're over the equilibrium, the delta S has to be over zero because you need additional energy to complete these steps. So I want you to look at figure 20.13. You will see three scenarios. I want you to discuss with your partner about its physical meanings. You have to recognize the second laws because we call it a law, right? So it has to override your perceptions. So that generally describes, in order to satisfy the second law of thermodynamics, your entropy of your universe, which means your system plus surrounding, has to be bigger than zero. So their relative value, regardless positive or negative, we're looking at it as a whole. So that means for a reaction or a process to become feasible, S delta change in its entropy has to be bigger than zero. These also explain why we generally consider heat as Le Chatelier principle. We consider heat as a product. Okay, we know because Le Chatelier principle is more of a descriptive, a qualitative picture of what's happening. So when we're doing thermochemistry, we actually care about the value of these enthalpic and entropic contributions. Okay, so next, at the end of last lecture, we briefly mentioned about delta G, the Gibbs-free energy. And so what is Gibbs-free energy? So it is a more quantitative way to describe the energy transfer within a system. There is the enthalpy, the delta H term, and the delta S, a change in entropy that accounts for the increase or decrease in your freedom of motions of your particles. So Gibbs free energy, this delta G equal to delta H minus T delta S, it basically describes the maximum amount of non-expansion work that can be extracted from a thermodynamically closed system. So what is a thermodynamically closed system? That means there's no exchange of matter, just simply the heat or entropy, okay? And then under some assumption, such as constant pressure, these terms are interchangeable. Because remember, delta S equal to Q over T. So actually, the Hosea Willard Gibbs, he is an American scientist. He came up with this concept of free energy. And so he was actually the first PhD in engineering that's awarded from Yale. And we know Yale is a very prestigious school, and actually his dad is a professor at Yale as well. But back in the days, about 150 years ago, education is a privilege for certain people. Not many people can actually go to school at the time to get a college degree or a PhD. So he actually founded the field called statistical mechanics, and that's what you saw previously to describe the ensemble of different microstates, and it's much more complicated than that. So I think in physical chemistry and electrophysics, you guys will deal with statistical mechanics at some point. And his work really provides a solid theoretical foundation for physical chemistry and describing chemical and electrochemical systems. So next lecture, we'll talk about more thermodynamics of battery system. And a little bit more about Gibbs. He started at Yale at the age of 15, and he got his PhD degree at the age of 24. The reason why he did not get the Nobel Prize is Nobel Prize doesn't exist at his time. The establishment of Nobel Prize occurs much later, okay? And then based on his work, a lot more European scientists were able to get Nobel Prize based on the study of various types of systems. He is the first one that combined the first law and second law. Does everyone remember what the first law is all about? Conservation of energy. He actually looked at these systems as a whole. So let's talk about car and battery. If you consider a car and the road as a system together, the chemical energy produced by burning the fuel, the gasoline, what kind of mechanism can the energy be consumed? So when we break down the gasoline, talk about what kind of mechanism will consume such an energy besides driving, letting your car move. I think you can list out at least 3 or 5 of them, right? So how many of you get the friction, the work done by the tire to the road, right? So that generally is in the form of heat. So we know when we run the car, the engine is pretty hot. So that is a release of energy from your car to the surrounding. What else? You have air conditioning in your car, right? So that also consumes some of the energy. And then when your car is driving, you will feel the resistance from the wind, and that also consumes some energy. It's a very complex system. So I want you to go home and think about battery. What could happen when we are talking about charging and discharging a battery? And we'll come back to this concept in the next lecture. So here is a list of energy conversion processes. We know that we can convert mechanical energy to electrical energy by knowing a little bit of electromagnetism. And it can be very efficient. And we can think about chemical battery. The efficiency is about 90, and then the efficiency decreases as you go down. Think about fluorescent light bulbs. Like these light bulbs, we put electricity in, it converts it into light, right? But the efficiency is quite low. And the rest of them is released to the surrounding in the form of heat. So that's the most common way to convert the energy. So this is just to put into perspective of different things. Okay, so let's talk about vaporization of water. We can quantify delta. When we boil water, we can quantify the change in its entropy. So if we look at the vaporization, under our perfect system, we can get the delta S from the heat of vaporization, then we can get a value from this. Okay, so if we plug it into this equation, the delta G is equal to delta H minus T delta S. We'll derive this equation in a little bit. So from this calculation, we can get at 100 degrees, it is at equilibrium. The energy required to vaporization offsets the increase in disorder of the system. So your delta G is equal to 0, it's at equilibrium, okay? So if we consider a system where we superheat the water to 110 degrees and all of a sudden open up your lid for this sealed container, because we know we need to get to, if we want to heat up the water above its 100 degrees C boiling point at 1 atmosphere, we have to pressurize our system, right? We do work to the system to force it so that the entropy is reduced and you have higher energy. So we get a negative value for your delta G. So that means when you remove the lid of the system, the water will boil immediately, because that explained if for a sealed container, if you have a lot of gas in it, the pressure will build up eventually and cause explosion. So now we will do some derivation of where this equation actually comes from. So for your entropy of your system plus surrounding. And we know at constant pressure, we can get the delta S of surrounding. It's equal to the heat or your enthalpy that you put into your surrounding from your system. So if we substituted this term into this equation, and then we multiply negative T on both sides of your equation, then you will get this equation. Okay. And then from the initial equation that it come up by Gibbs, he generally said the delta G, the delta just means the change, right? But from the Gibbs initial equation, it's G equal to H minus temperature times your entropy, right? So we can get that this term could become your delta G of your system. And then that's where this delta G equal to delta H minus T delta S come from. Okay, so according to the second law, the delta G, if it's less than 0, then it's a spontaneous process. And then we will do final minus initial. In the previous example, we talked about efficiency. Delta G generally estimate the maximum amount of energy that you could have. But a lot of time, you will lose some of the energy of your system to the surrounding, okay? So for a case where delta G is larger than 0, that means it's a non-spontaneous process. You have to put in additional work into it so this reaction could occur. Let's get back to this example here. If we plotted the change of your delta H and change of your delta S as a function of temperature, noting that there's no little circle, so it's not under the center state, then therefore your value could change, okay? And then there's a crossover point where your delta G is equal to 0. So it's a balance between your enthalpic and entropic contribution. This process, whether a reaction process is spontaneous or not, is related to the specific reaction that you're looking at or specific process that you're looking at. For example, when we go over this critical T, your delta G, your T delta S dominates the equation, right? So your vaporization becomes an energetically favorable process. Then for every process, there can be different values. Let's look at the first one, that is a temperature independent process. Okay, so for the decomposition of hydrogen peroxide, we know it happens readily. If you have a bottle of hydrogen peroxide left there for a long time, it will eventually decompose completely. That is because it's delta H and delta S. One is negative and one is positive. And we know temperature is always positive. So when we have a negative term, added another negative term, you get a more negative value. And there are also certain processes that are non-spontaneous at all temperature, such as conversion of oxygen into ozone. So if we look at, you have a positive delta H, that means you need to absorb energy for this process to happen. And at delta S, it becomes less random, less disorder. So we know that's bad. Such process is very difficult to trigger. Okay, so let's consider another case. Oh, one thing I want to point out is recognize the difference in the unit. Okay, so when you do calculation, be very careful. You have to make sure you're either in kilojoule or everything is in joule. So for such a process, we can calculate your delta H is positive, right? So when your delta T is high enough, then this delta G value will become negative. So if you're doing a simple math, if you're setting this delta G equal to 0, you can solve for that T, which is the crossover point that you saw previously. Okay, so when your T is about 1,000 K, then this process becomes energetically favored, as determined by delta G. In another case, let's look at oxidation of iron. So from the battery session that we talk about, that we have a standard electrode potential, and from that we can conclude, okay, iron readily oxidizes. So a lot of metal, it will have a thin layer of oxide present on the surface. But why? That's because the oxidation process is energetically favorable. And if you want to reverse it, you have to go to a very, very high temperature. So if you do the math, okay, if we think about the delta H, it's an exothermic process. It's generally from high school, we know that for exothermic reaction, we know generally it's a feasible reaction. And then because usually these type of reaction, the contribution by the entropy is generally small in comparison to the enthalpy. So that's why a lot of time we would think of exothermic reaction is preferred. The delta S, we know we combine more molecule into less molecule. So that means we have, no, actually that's not right. Okay. So generally for this process, overall consider all the possible motion of iron or oxygen in comparison to iron oxide, you become less disorder. So let's look at how this gift-free energy process can be applied to the biological system. So you will also hear entropy in information science, okay, in biology, they all talk about entropy. So ATP, this molecule on the left, is what cell or the living system use to trigger or to capture energy, to gain energy from. Usually our body or the cell will store a lot of ATP, right? So when it requires energy to conduct a chemical reaction, it will utilize enzyme to break down this ATP molecule to ADP molecule. And then there is a supplemental reading in your book to talk about why such process is feasible. But the more important part is that for each mole of your ATP, once it's been broken down, it's 30.5 kilojoule. Okay, so if you think about it in calorie, it's a lot of calorie. So we know there's a conversion between calorie and joule. And now we're in kilojoule regime for 1 mole of ATP. For a lot of biochemical reaction, it will utilize ATP as its energy source. So one example is the breakdown of glucose. We consume, such as rice, our body have these enzymes to break it down to simple saccharides, and then some of those will be glucose. So when we consume food, we will convert these ADP molecule to ATP. So we store the energy in a form ATP. So this is the recycling of your ATP and ADP molecule in your body. When we eat food, we can consider it as an oxidation process of food, whatever that food is, right? And during that process, we gain energy. So we utilize this energy to do reaction so you can put another phosphate molecule onto your ADP. And then when you require energy, you will convert that ATP to ADP that will generate phosphate and this ADP molecules. And then there's multiple things that you can do. There's a very important biochemical pathway inside our bodies. So for example, I'm moving my arm, that is converting ATP. So when you are exhausted, generally that means your ATP is not enough, right? So your body sends out this signal to part of your brain telling you're tired or you're hungry, okay? So we want to restore that equilibrium. So this is just to put biology context into this work. You can think of the biological system, it can be described by thermodynamic terms. So we consume food, and a lot of these energy is used on maintaining the basic life function, right? Such as breathing. Just by being alive, you consume a lot of energy. Previously, we talked about enzyme catalyzed reaction, right? So now I want you guys to get into the group to see if you can figure it out. Why does the reaction rate become lower once your temperature increase? And also describe why does the pH change will affect the reaction rate. So think of it as in the term of ATP consumption and ADP production. Okay, so from the previous chapter, we know enzyme can act like a catalyst to accelerate reaction, right? So enzyme is a protein, and it's require energy to drive biochemical reaction, right? So generally, when we increase the temperature, these protein or these enzyme will be denatured, so it loses its activity. So that's why you see a decline of its reaction rate or activity at higher temperature. And same thing happen at lower temperature. It's less likely for the enzyme to actually bind to a substrate to undergo the subsequent reaction. How it is related to the delta G. I mean, the delta H and delta S of these processes generally doesn't change, right? And then so we can look at this delta G is equal to delta H minus T delta S. When we have a very small change in its temperature, we can describe what's happening in this region, okay? And also, why does the pH matters? So this has to do with the concept of previous chapter. Proteins are made with amino acid, right? So the pH will affect how many nitrogen or the amine group and carboxylic acid are protonated or deprotonated, right? So when you change the pH, you will change the charge, the amount of charges that are present along the protein backbone. We know the protein has to fold in certain way, right? So when you change the pH, this operation range, it will change its configuration and it lose activity. It cannot undergo reaction, okay? And then why does protein denature? We can also look at enzyme or proteins folding process with this delta G, right? When you fold, you form these hydrogen bonding at certain places, you will get a certain enthalpic contribution and entropic contribution, right? So if we think about unfolding DNA or unfolding protein, its entropy will change upon folding them into the correct conformation. And so there's a lot of genetic disease that has to do with misfolding of proteins. Then it really depending on your disease state. The disease can cause a change of your delta H and delta S term for these proteins, and these parameter change will affect whether a process is spontaneous or non-spontaneous. But being spontaneous or non-spontaneous doesn't mean it will happen readily, okay? That's a very important concept you have to remember. So for enzyme catalytic reaction in biochemistry, you will learn more about it. It has to do with availability, other substrates, or the energy input such as ATP and ADP, because when you change the pH or you change the temperature, you will affect a lot of pathway. Okay, so our biological system is a much complex system. Okay, so now we'll get to the next part. From this equation, we can figure it out the effect of temperature, whether a reaction is spontaneous or not. We can figure out the crossover point by assuming delta G is equal to 0, then you will get, okay? So as I mentioned before, in the gas phase, your entropy will have more contribution, right? There's more freedom. So remember PV equal to nRT? We can also rewrite this equation so that we consider the expansion of gas, which it does work to your system. Based on its pressure change, you will do work, right? So we express the delta G in this way. When the delta T is 0, your delta G will equal to the change of pressure. So if we put in the PV equal to nRT, and then we can get your change of your free energy state. So your product gives free energy. Your reagent has to give free energy. You can rearrange the equation and get this as a change in pressure and how that related to the change of your gives free energy. So we can integrate and rearrange and get this, because remember Kp when we are talking about a reaction quotient, right? So your equilibrium constant is product over reactant, and whatever amount of the stoichiometric factor that you have become the power law of your partial pressure, right? Then you can get this equation of delta G equal to negative RTLN, which is equilibrium. And then by adapting this equation, we can get your Kp. You can transition from Kp, which is the pressure term, to the concentration term of an equilibrium constant. So basically, you can use equilibrium constant by adapting this equation. You can calculate whether a reaction is energetically favorable or not. Because when we're talking about equilibrium, we generally do not discuss thermodynamics of a reaction. But we know when we're producing a lot of products, right, you have a larger K value, then you get a more negative delta G term. That means the reaction is more favored. When you're having a very little product, depending on how you write down your rate expression, then that means this process is not favorable. And at infinite time, then you can ask whether this reaction is energetically favorable or not with this simple equation, and that will give you some clue to describe the state of the reaction. So we'll go back to reaction quotient. That's a reminder from the previous chapter of a reaction quotient. So it's basically to describe the state of your system. You can see it as a microstate, one possibility of many states when you mix reagent together. There are many things that could happen, right? It can remain unreacted, or it can undergo multiple equilibrium if you have a multi-component reaction, right? Okay, so reaction quotient is a quantity, a parameter that describes the relative amount of your product or reaction at a particular time. When Q is equal to K, that means you're at equilibrium. Okay, so when you're below, what does that mean? When it's above? Okay, so you can generally relate this to gets free energy. Okay, so that is the reason why how we define the relative value of Q and K and to decide whether your reaction is at equilibrium or not. Okay, so this is another way to get such equation. So at standard state, your Q is equal to 1. So let's look at sample problem 20.9. That should be a relative simple mathematical manipulation, right? So by adapting this equation, you can easily figure out what is your equilibrium constant and what is your delta G. Yeah, and then for this chapter, you need to be able to calculate your delta S, and under certain condition, you can get delta G from delta S, right? So you just do the same mathematical calculation where you can get delta G based on the delta G formation. So when you read this textbook, that will make more sense. And in your appendix B, in the back of your book, it has a lot of parameters for most common substance, okay? So I would encourage you to learning how to look up this table. Okay, it's pretty straightforward, right? It's just knowing which equation. I don't think there's any new things here. The calculation is very similar, right? So now I want you guys to get into a group, discuss with your partner. So let's look at the first problem to determine whether a process is reversible or not reversible. The related definition, if you actually did read the book from the 20.1 to 20.3, you should be able to answer this question. A neutralization reaction, that means you're mixing acid and base to get to pH 7, okay? So you just need it for 1, 2, 3. So you can just say A1, A2, A3, A4, okay? Just write down it's reversible or irreversible. Talk to your partner, okay? If you're not sure, you can state why. Okay, so the first one, it has to do with delta S, okay? If you're not sure, it has to do with the laws of thermodynamics. So look at your textbook. Okay, if you have already finished the first one, now we can move to problem B. So the B, I want you guys to think about what do they mean by dissolved, okay? And then try to relate it, solubility, the concept of KSP to the Gibbs free energy. Now you see how all these chapters, they are somewhat interconnected, right? So being completely miscible, you can understand that its ratio can be from like the aniline to alcohol ratio, ethanol ratio can be 1 to 100 or 1,000 to 1, right? That's what it means by completely miscible. It means they mix well. Okay, so the problem C is a very classical problem that were commonly claimed back in the 1920s, okay, when the car first emerged as a new transportation. Okay, so the reason why people come up with the explanation of thermodynamics, part of it is to try to understand how the combustion engine works. How do we make it more efficient? Okay, so then sometimes people will claim they have a machine that will continue to run endlessly. Okay, so think about the laws of thermodynamics. Okay, try to explain that. So perpetual motion machine, that means once it starts, it will never end. It kind of agrees with Newton's law, right? So this is the type of problem that would appear on the finals, okay? And then this is like the Carter core knowledge. You need to be able to do these mathematical calculations. This class, I really want to focus on concepts, but with the concept in hand, you should be able to run these calculations, all right? So I know you guys don't have enough time to work on this problem, so you don't have to turn it in because I already assigned homework. Okay, so please read chapter 20. We will continue discuss different aspects of chapter 20 on Friday. 下课。